Welcome back. The topic this week, as you can see from the overview of the week, is to start with Hartree-Fock theory and go through the derivation of some of the equations. And yesterday, what we did was to give a general motivation. And what we are going to show today, and we actually did that yesterday, but we did that in configuration space, was to show that we can actually define a new set of single particle states, which are eigenstates with the corresponding eigenvalues to a new single particle Hamiltonian. This is a single particle Hamiltonian which will optimize the energy of the system, and it's going to hopefully give us an energy which is getting closer to the true energy. We don't know that. So unless you know what the energy should be, most likely you will get something which is approaching a global minimum. Probably you will be in a local minimum, which is better than the one which is derived from your reference state. And the reference state is typically a basis which you would choose to be an eigenbasis of the kinetic energy plus the external potential. So the external potential, if you look at it, and for those of you who may be following a course in nuclear physics, there are many ad hoc type of potentials which are fit to experimental data. There is one which is called the Saxon potential. We've met the harmonic oscillator. We also have what from atomic physics, we have the potential which is set up by the atomic nucleus, which confines the motion of the electrons around an atom, an atomic nucleus. Now, these potentials, which you see here, are in some cases artificial. In some cases, we can actually claim that these come from some features of the problem, like the potential which is set up, the attractive Coulomb potential, which is set up by the atomic nucleus. So if you only have this, you wouldn't correct the motion of, let's say, the electrons in an atom like neon by the presence of the other electrons. So what we are doing now is to actually derive a new set of equations using the variational principle, where we now have a modified single particle Hamiltonian. And you can see now this modification brings in a new potential, which is an effective potential, calculated from the interaction which we have. And in this case, the way you can read this is that every single particle sees a field which is set up by the particles below the Fermi level. And clearly it cannot interact with itself. And in the case when this I is equal to one of these P's and Q's, then the contribution from the anti-symmetrized matrix elements is exactly equal to 0. So the way you can read this now is that you're setting up a new mean field. Previously, we had a field which had no knowledge of the system. And we normally called this contribution here for a density-dependent contribution, because it depends on the specific system you're looking at. And yesterday, we could actually rewrite parts of that interaction in terms of the direct term, and then we had this exchange term, or what we normally call the Hartree term and the Fock term. And the Hartree term is a term which we can rewrite in terms of the density, which is given by the expectation value of the single particle states below the Fermi level, the sum of these. And that means that what we see now in these equations is a modification of the single particle wave functions. So there are still many-body correlations which are missing, but we are now bringing in some many-body correlations due to the fact that we have the potential between two electrons here. And actually, in principle, this is a sum of all the electrons which are present. So we went through, we have a reminder of the variational principle. And what we did yesterday was actually to derive the equation in coordinate space using the variational principle. And we ended up with a new Hamiltonian in coordinate space, which now contains one, the standard kinetic energy plus external potential. And then there is a term which is defined by the exchange piece. And if you look in the direct piece, so this is the direct piece, So this potential here, it contains the bystanding particles in quantum states mu here, and you see we are summing over them here. And this function here multiplied with this function is the wave function squared for single particle state, and that enters the definition of the density of the system. So normally we call this a density-dependent term. In a theory which is called density functional theory, which we will discuss a little bit later, then it's common to approximate this with simpler equations and then rewrite everything in terms of the density. We're coming back to this. This term is the exchange term, and this is the term which brings in the nonlinearity. What you can say now is that you brought in a specific type of many-body correlations. And these correlations are given now by the interactions between the bystanding particle and all the states in the Fermi level, below the Fermi level. And you can see now that we have a sum here over the mu's, and these are all the particles which fill up to the Fermi level. And we have a direct term and an exchange term. And these two terms, which you see here, they define this Hartree-Fock potential. And this first term is then the kinetic energy and the eventual external potential which we have. If you're dealing with nuclear physics, for instance, then there is no external trapping potential. And in principle, you should not have an external potential, but many people apply one just to bring in a handy single particle basis. But then you would just have kinetic energy plus the Hartree-Fock potential. Now, what we are going to look at now is the Hartree-Fock by varying the coefficients. The problem here, when you look at the equations, when you're solving Schrödinger's equation, you can see this equation 3 here is the one which now represents the modified Schrödinger equation. So we would have now the kinetic energy, we can have the potential energy, we have the direct term and the exchange term here. So if we leave out the external potential, we would just have kinetic energy here. And then this is the new equation of motion which we have to solve. And when you multiply with the psi mu on complex conjugate on the bra side and integrate, you actually have to evaluate these integrals in order to get the energy. And this is something which can be time consuming because you may need many integration points to get an answer which converges. So the alternative is actually to pre-calculate these matrix elements in a given basis, and then just instead of us now varying the wave function itself as we did yesterday, because yesterday what we did was to take the single particle wave functions here and vary them. Now what we're going to do is to vary the coefficients of a linear expansion in terms of a chosen basis. And this leads to, from a computational point of view, a much more efficient way of solving the equations. But it requires that you can tabulate that, or that you have tabulated the equations before, the integrals. And the basis, if we now choose a orthonormal basis and we perform a unitary transformation, as you can see from the basic linear algebra here, and I invited you yesterday to just take a look at it. When you look at that, what you have now is that the new basis is going to be given in terms of a unitary matrix element times the previous basis. And the new basis is also going to be orthonormal if the previous basis is orthonormal, and we are performing a unitary operation. So this is the way you can view now the Hartree-Fock equations. Now, there's another thing which I mentioned, which is you have most likely seen in one of the exercises, is that the Slater determinant which we have is based on a linear expansion in terms of the orthonormal basis. So this basis phi here is something which we know how to calculate. We may have analytical expressions for it. It could be hydrogen-like wave functions. It could be harmonic oscillator wave functions. And these are often handy functions because you can, for instance, for the kinetic energy and for the external potential, you have analytical expressions. And if you plug in these states or state functions in the calculation of a two-body matrix element, sometimes it happens that you have analytical expressions, or you have recurrence equations, which can then be used in an iterative way to calculate the expression you need. So that means that you can calculate some of these on the fly while you're performing the computation. So what we are going to do now is actually vary these coefficients here. And the Slater determinant which we have is a Slater determinant now, which is given in terms of these coefficients. And you can rewrite that as two matrices. The matrix C, which is a unitary matrix, and the previous Slater determinant. So when you calculate the determinant, you know that the determinant of the two matrices is equal to the determinant of one of them multiplied with the other. So it means that the new Slater determinant is proportional with the previous one by the determinant of a unitary matrix. So that's one way of reading what we are doing now from a mathematical point of view. It means also that when we now perform the calculations, in the previous wave function, the previous ansatz for the ground state, this was given by the sum of all the single particle states up to the Fermi level. And we are going to get the same type of equation when we now introduce the new basis. Except that now the new basis may not be an eigenbasis of this H0 which we have. So let's go back to the whiteboard, because this is basically where we ended yesterday. And so let's write down some of the basic equations which we need to look at now and how we are going to perform the calculations. And then we are going to look at interpretations. And after this first lecture, we are going to look at the Lipkin model again, which is one of the exercises for next week, and then see how we can perform a Hartree-Fock calculation on the Lipkin model. And the Lipkin model is a very, useful model, because it allows us to get analytical expressions. And we can say something about the constraints on the matrix elements and the stability of the Hartree-Fock equations. So this is extremely useful before we, next week, jump into a more formal definition of the stability of the Hartree-Fock equations. So let's now go back to the whiteboard and take a closer look at the equations which we want to calculate now.
In previous exercises for the Lipkin model, I remember that we constrained some states to not happen, right?
In the Hamiltonian, we only look at specific excitations.
Yeah. Does that have anything to do with fixing some matrix terms to zero?
Yes, exactly. So the type of excitations, we could not have 4-particle 4-hole excitation or 3-particle 3-hole excitations. And we had only some selected 1-particle 1-hole, 2-particle 2-hole excitations. And that simplifies all the calculations. And the matrix then, we got this 5x5 matrix last week, and that makes it much easier to actually set up the Hamiltonian problem to diagonalize and also solve the Hartree-Fock equation.
So that was related to what we saw last
Yes, yes. So you can always limit your two-body interaction and say that you only allow some specific excitations. So later we are going to encounter another model, which is called the pairing model. And in that case, we can only promote pairs of particles with opposite spins. And that is a model which was used by Bardeen, Cooper, and Schrieffer to explain superconductivity. So that's a model which is extremely popular in physics, in condensed matter physics, in the physics of quantum liquids, like superfluid helium, and also in nuclear physics, where pairing correlations play an important role due to the strength of the interaction and the shape of the interaction. Now, so let's remind ourselves quickly of what we have done. So what we have now, when we look at the Hartree-Fock theory, what we want to do is to vary the coefficients. So we have a basis set, psi p, which we now want to expand, and I'm leaving out the spatial degrees of freedom. And we want to expand this in terms of a matrix, Cp lambda, and then we have our original basis. And we have assumed that this basis, I should actually use small letters here because I reserve the uppercase letters for the many-body states. So what we have then, is a orthogonality requirement of sigma, and that is given by delta lambda sigma. And this means that if this is an orthogonal basis, and we assume that's sort of normalized, as you can see, then, and this means that if I calculate the overlap with two states here, this is also equal to delta PQ here. So we have an orthogonal basis. Now, the original basis which we had, quickly remind you of these things, this lambda basis is now an eigenbasis of the Hamiltonian H0. However, the new basis is now assumed to be an eigenbasis of the Hartree-Fock Hamiltonian. And let me just quickly remind you of that one. So I'm going to put a label HF on that, just to distinguish it from the original unperturbed basis. So normally that's called an unperturbed basis because there's no information about the interaction between the particles. So the Hartree-Fock basis now includes the interaction between the particles below the Fermi level, and that sets up a mean field in which the particles are. Let me just rewrite this a bit better. Then what we have is a Slater determinant phi 0, which is now given in terms of the Greek labeled basis set. And in that specific case, we have a 1 over n. And we have a sum. I'm just repeating these things here, just for the sake of completeness. Then we have the product of all these single particle states. So we have a lambda 1, lambda 2, etc., up to a phi of lambda n. And these are the states below the Fermi levels, which are occupied. And we are going to do the same with the p's. So the new Slater determinant, we call this psi 0 here, is now going to be given by the new basis set of p of -1, all the possible permutations, and then I have the psi p1, psi p2, up to psi of p of n. So the number of single particle states is the same as before. So this Slater determinant, which you have here, is based on a matrix, which is an n times n matrix, and the same with phi 0. So the two objects are now the different ansatses for the ground state. And here, we should now put this HF here. So I'm going to, in general, to put an HF here to indicate that these are the Hartree-Fock states. So if I take these two Slater determinants, and it's pretty easy to calculate the contribution to the energy. So if I do that one, this is something we calculated in the very beginning of the semester. So this is now given by the sum over all the states below the Fermi level. And then we have this compact notation here, we have H0 times mu. And then we have plus a sum over a double sum with no restrictions, because the matrix elements, which would be diagonal here, they zero out due to the consequences of the Pauli principle. And we would write this as a mu of V. This is the interaction term of mu nu anti-symmetrized. Like this. So this is now, if I calculate the expectation value of the Hamiltonian with respect to the original Slater determinant.
But since you are summing freely, why are you dividing by a half?
Because the original equation was given by a sum where I had a mu less than nu.
Yeah. Oh yeah, it's the other way around.
So you just double count. So you can put in a restriction, and then have mu less than mu, or you can just sum freely. Now, when you're doing this numerically, summing freely is a waste of cycles because the problem is it's a Hermitian problem, and that means that the matrix elements will be the same. But this is just a compact way. So you can choose whether you want to have this notation or whether you want to have this specific notation. So when you sum without restrictions, you're actually doing some doubling, which is not very efficient computation. But sometimes you will be surprised because, and this was a big, how to say, big disappointment for my side when I first did it. So I've been doing many body perturbation theory for many years and couple cluster theory. And I would then, when I was calculating contributions to the energy, I would put in all the physics constraints which I could, symmetries and so on. That leads to a lot of if tests when you write the code. But then I would not sum freely. When I took away all the if tests, and the only thing I did was to have a table of matrix elements which were allowed. So there would be many zeros. From a computational point of view, that was more efficient than having all the if tests. So that in a way, that's a little bit disappointing. So you may think that computationally this is better, but it could happen that just setting up the calculations freely without any if tests or any go-to statements if you're writing a fault.
Where do you mean, like with sparse matrix?
As a matrix is sparse in general. And then you would use matrix, the algorithms with sparse matrices.
Because there are some optimizations.
Yeah, exactly. And the thing is that you can actually rewrite many of these contributions as matrix multiplications. And they can be done efficiently on parallel high-performance computing facilities. And then you don't have any, because when you run in parallel, you don't want to have any if tests. An if test means that the parallelization or the optimization normally breaks down. So this is something to think of from a computational point of view. So I spent a lot of time implementing all the symmetries, all the possible physics, which I could put into the summations. And that actually slowed down the code. Yeah. The only thing you have to do is to have a table of matrix elements which respect the physics of the system. Okay. that's some disappointments.
Yeah.
Now, what is special here is that if you look at these matrix elements, this one with the basis you have, typically this will just become a number and you don't need to evaluate an integral because you have assumed that this basis is an eigenbasis of this H0. So typically what you would see is that this becomes equal to some sum over mu, and then you would simply have to look up in a table the values of these elements. So if you're doing atomic physics, you have analytical expressions. If you're doing the harmonic oscillators, you have analytical expressions, etc., etc. So just writing it up, mu, anti-symmetrized. Now what comes next now, and so the calculation here is actually agnostic to the type of single particle basis you've chosen. So if I use the new Slater determinant, I should get the same type of equation which you see here, this one, but with a new basis. So the calculation is exactly the same as before. The only difference is that you may not have this term. So if I now calculate the same expectation value with a new basis, so psi 0 Hartree-Fock of H, of psi 0 Hartree-Fock, what I get then, if I just repeat what we had in some of the first exercises, I get simply a sum, but now the states, which in my case are given by states below the Fermi level. So I would now have an I less than F up to the number of particles up to the Fermi level. Actually, this also runs up to the Fermi level is nu. And then I would have an I, and then I have my H0 of I. But now I have to be a little bit careful because this is not necessarily a basis of the Hamiltonian H Hartree-Fock. So then I need to leave it as it stands. And then I would have a new term where I have a sum over ij multiplied with a factor of a half. And then I have an ij, v, ij anti-symmetrized. So the equations, I mean, they cannot change in character, right? Because we are just calculating an expectation value. And when we calculate an expectation value, the sums which you see here, they are simply defined by the fact that now we have an expression for the wave function on the right-hand side and the left-hand side, which entails the same wave function. And then these are the equations which we have to set up. These states do not need to be states below the Fermi level. So these could be the states which are defined in each of these functions. But now we actually requiring that these are the states below the Fermi level. So what will typically happen then, if you now look at your basis sets, when you run the calculations, so this is your Fermi level, and then we have these states which we call mu1, and then we have mu2, etc., all the way up to mu of n. So these are the states which are filled. And we have a state here, a single particle state here, which is filled, and up to the top here. So when we run a calculation now, I mean, number of particles don't disappear. There is nothing in the Hamiltonian which deletes particles or annihilates particles. What will happen then is that the new single particle basis, so these are the energies. So this will be epsilon mu1, epsilon mu2. So everything is plotted with respect to an energy scale. What will happen now is that we actually get energies which are different, single particle energies, which may not be the same as what we had before. So this will be in minus 1, and here we start with I1, I2, I3, I4, etc. So these energies are still represented by the states below the Fermi level. So we assume now that when we run our calculation, that we are now having a state determinant where all these single particle states are occupied. But they may now be linear combinations of these other states which you see here. So if you now move up here, you would have a mu of n plus 1, etc. And what we are going to see when we solve the equations is that these new states will be linear combinations containing multiple Hall excitations. So just keep that in mind. Then you're setting up a Slater determinant where you fill up all the states up to the Fermi level. And this type of Slater determinant gives the same looking like equations, but the basis set changes. And also the new determinant, this det psi 0, Hartree-Fock, is something which we can rewrite as det over unitary transformation multiplied with the determinant from the previous answers. Okay, so what we are going to do now is to go back to the basis expansion which we did. So this expression which you see here, and now we're going to vary these coefficients. So let's do that. And what we're going to do now is actually to plug in these coefficients in the expressions which we have here. That makes sense? So let's now look at the calculation of the new energy. So we have the phi 0, no, not phi, but psi. So the Hartree-Fock expectation value, H of psi 0, Hartree-Fock. This is now going to be equal to the sum. And I'm going to have a sum now over alpha and beta. And now I'm summing freely. So remember now that when we look at this expansion on the top here, this sum over lambdas goes in principle over all possible single particle states which we have. Just keep that. So if we have an infinity, this runs over an infinity of states. But we will always truncate this from a 0 up to some number d. And that's going to define the dimensionality of the problem. So that means that these sums alpha beta, they run now over all the single particle states. And if we now look back at what we had this sum of i's here. And it means that in principle, I just need to just look at my small cheat sheet here so that I don't say anything wrong. Yeah. So I have if you now look at the expressions which we had, so there is a sum of I here. So we have a sum here, which we have to put up I, and these are states below the Fermi level. And that goes over the n single particle states. So that runs over all the states which we have here. Okay. And then I expand the single particle wave functions in terms of the original basis. So I would have a C of I of alpha complex conjugate. And I'm going to have a C of I of beta. And this is now multiplied with the old basis which I had, which in principle is an eigenbasis of this H0. If it is an eigenbasis, you could have chosen something which is not an eigenbasis. But this is very much up to you. And now pay attention to what we have next here. So we get now for the two-body interaction, there's a term ij, where we now sum over the particles which are present. But then we need to sum freely over the expansion. So the first sum goes over the size of the system, the number of particles which are present. So we are now having a sum here, a free sum, alpha, beta, gamma, delta. And then we have now coefficients C, I, alpha, C, J, beta, complex conjugate. And then I have a C, I, gamma. And then I have a C, J, delta. And this is now multiplied with the final matrix elements, alpha or beta or V or gamma and delta, and this is anti-symmetrized. So this is now the same object as we had here, but now expressed in terms of the basis we started with, which could be a physically motivated basis, a handy basis from a calculational point of view. And what you will see now typically is that these matrix elements, they would now typically be pre-calculated. And the same with this one. So these matrix elements, they are normally pre-calculated and tabulated. And tabulate. So that means that what you're going to have then is a problem where when you're now running over the indices here, you simply need to look up in a table, and then some of these matrix elements can be zero, and some of them do not need to be zero. That will be defined by the specific problem you're looking at. And then you would have the indices alpha, beta, gamma, delta, and you would look up the indices. So that's the equation we're going to start with. And now we're going to take the functional derivatives. And when we take the functional derivatives, we can now look at, as we did for the coordinate space equations, we can now just look at one of these. So we can pick now a Ci alpha and take the derivative with respect to the complex one. So this is now going to be my expression for the energy. So this is my E0 Hartree-Fock, which is going to be my reference energy. Now, another constraint which I have is the constraint of orthogonality. And that's going to give rise to these Lagrangian multipliers, which we need to add into the equations. So the final function which we are going now to optimize, so the functional to optimize, so let me just write this down here. is the following function. So it's a d, and I'm going to take the derivative with respect to the ci alpha. And for every I, we're going to have an equation. And if we have I from 1 to 10, there will be 10 lines which we have to solve, or 10 equations which need to be solved. And what we want to calculate now is a functional of f of psi 0 Hartree-Fock, where this f of psi 0 Hartree-Fock is now given by this E0 Hartree-Fock, which we have set up. So this means this expression here. And then we have an orthogonality condition, which has to be applied to the equations. So this is going to be a sum over my I equal 1 up to n. There is a Lagrangian multiplier, epsilon I. Then I have my sum over alphas here. And then I have a Ci alpha multiplied with a Ci alpha, because it has to be orthogonal. The original basis is orthogonal. So previously I could have had a sum of alpha and beta, but since my original basis, alpha and beta, is orthogonal and normalized, then the double sum which you would have had here disappears. So what we have to do now is to take these derivatives with respect to each Ci alpha. And since we can make these problems independent for the Hermitian conjugate and the non-Hermitian conjugate term, we just look at the one for the Ci alphas. So if we take the derivatives now, we go back to the equation here. So the first term, and now we are taking away the sum over I, because we're looking at an explicit I. So for one specific I, so for a specific I and a specific alpha, Ci alpha, then we are actually getting an equation which is going to look like this. So I will have sum over beta, if we go back to the expression, and then I'm going to have a Ci beta, and this is multiplied with the matrix elements where I have alpha, H0, or beta. So that will be that term. Now, when I'm looking now at the second term, which we have set up here, this term here, when I pick a Ci alpha, I have to be a bit careful, as we discussed last time, because we have a Ci alpha here. And since we are running freely over alpha and beta, we may actually hit one which has the same accuracy. And then, as we did yesterday, we are going to get two terms. So that means that the factor of a half disappears, when we just use also the symmetries of the interactions. And the fact that the alpha, beta, gamma, and delta are just dummy indices. So that means that when I look at that term, the derivative of that, I get a plus. Sorry. I have a plus here, and then I have a sum over j. So that has to be that, less than the Fermi level. And then I have now the coefficients. So there's going to be a coefficient Cj complex conjugate of beta. I'm going to have a Ci delta. I'm going to have a Cj, so it's actually gamma. This is a delta. And this is multiplied with a matrix element alpha, beta, V, gamma, delta, anti-symmetrized. And then we have minus term here, which now runs simply over the alphas, but this is simply going to be equal to lambda of I multiplied with Ci alpha. Okay, so if you now look at the equations which we have, there is nothing which hinders us now from changing these equations here, because if you look at the sum over betas, and we also have this sum of, so there should be a sum here over beta, gamma, and delta. Sorry, I forgot that sum there. We can now rewrite this equation here in terms of the following. If we now define a specific object, so I'm now going to define an object which I'm going to call alpha beta here, Hartree-Fock. And that is going to be given by the following. It's going to contain alpha of H0 beta. That's the first term. And if we have assumed that alpha and beta are eigenbasis, is an eigenbasis of H0, then this just becomes equal to a simple constant. It is a constant, but we know exactly what it is. And we don't need to evaluate anything, we can just pre-calculate it. But then we are now going to, if I introduce it, I'm going to take the sum over the j's, less than f. So that's going to be there. And then I have a sum over gamma and delta. So I'm just going to keep that one. And this is multiplied with a c. So what I'm doing in these equations here, I'm going now to interchange the terms which I have. Since these are just dummy variables, I'm going to interchange beta with this term gamma here. So I'm just going to change the labeling here. Because then what I'm going to have then is, if you look at this term here, I will now have a term which has a ci beta here instead of a ci gamma. But then I will have a beta here and I will have a gamma here. So remember now, these are just dummy variables. So what I want is to have something where I can single out a sum of a ci beta. Okay? And remember, these are just dummy variables, right? So what I get then is a new quantity here, which looks like, since I have my j, so I have j and gamma, complex conjugate. And then I have a c of j, of delta. And then I have a matrix element, alpha. But now I have to be a little bit careful because I interchange gamma and beta of b. And now I have beta of beta and delta here. Does that seem plausible? So the only thing I did, so I'm now picking out this term here. So that's why I don't have the coefficient here. I just relabel this to make analysis so that I can actually single out the ci beta. So if I do that, and you see now this looks like my Hartree-Fock Hamiltonian, which we decided upon, then I can rewrite my equations in the following way. So what I can have done is a sum over the terms j below the Fermi level. So if you go up here, and then just let me just note that one. I can rewrite this in terms of a sum over beta, like that. And this has a ci beta multiplied with these matrix elements, which we can pre-calculate if I know the parameters c, the coefficients. And if we now look at the right-hand side, what I will have is a lambda y of ci alpha. And this is nothing but an eigenvalue problem, which I can then translate into this Hartree-Fock matrix, or Hartree-Fock operator, which we call it, or now a matrix. And this is multiplied with the coefficient c, and that gives an eigenvalue multiplied with the coefficient c. So in this case, what we have done is to rewrite the variational principle equations we get in terms of a matrix eigenvalue problem. And where the coefficient c now are the eigenvalues, eigenvectors obtained by diagonalizing the Hartree-Fock matrix. And this Hartree-Fock matrix will have these specific matrix elements. And you can see now that before we take a small break now, if H0 alpha or beta is equal to a coefficient epsilon alpha times delta alpha beta, that is going to simplify the calculation of the matrix elements. And this is a pretty common choice. You don't need to have it, but it's a pretty common choice. And then you see now that in order to find the coefficients, we need to solve this in an iterative way because we don't know the coefficients. So we need to start with a guess. But this is in essence the Hartree-Fock method, and it's much easier to derive when you look at the expansion in terms of the coefficients of the wave function. And then the only thing you need to do then is to have a diagonalization problem. And even if you have 10,000 single particle states, every iteration involves just a diagonalization of a 10,000 times 10,000 matrix, which can be done pretty efficiently. And a basis with 10,000 matrix elements is a monstrous basis in all many-body calculations. So typical many-body calculations, they deal with 100 to 1,000 single particle states at most. So that means that the matrix you need to diagonalize is 1,000 by 1,000. And you can calculate often these matrix elements which you see here. These can be calculated rather precisely if you have a basis which is optimal for that specific Hamiltonian. So the harmonic oscillator or the Schrödinger type wave equations, we have analytical expressions for these. And also if we have a Coulomb interaction and we put in a harmonic oscillator basis, we can find analytical expressions. If we have a hydrogen-like basis, we also have analytical expressions for many of the matrices.
But what is the advantage of this over the varying the wave functions?
You mean the original one?
Yeah, because first we varied the wave functions, and we also got the eigenvalue problem, right?
You got an eigenvalue, but then you have to evaluate the integrals every time.
Oh yeah, that was the wave function. And that involves many data points.
And that normally is something which can be numerically time consuming. And you can also get, due to the kinetic energy, which is often sensitive to the tails of the wave function, you can actually run into a situation where you need tons of integration points. And that can slow down the calculations. Whereas now the advantage here is if you can pre-calculate these matrix elements, there's always a trade-off. If it's too complicated to pre-calculate them, and you have a recipe for calculating on the fly when you need them, then you would use that recipe. So we had once a master student who did a PhD in quantum chemistry. And what he did was actually to set up these recursion relations for specific basis sets, this Gaussian basis set, which is very popular in quantum chemistry, so that you could calculate the matrix elements on the fly. That was very tailored to a specific problem. So many practitioners, unless this table here becomes gigantic. So if it takes days to produce that table, then there's always a trade-off. Actually, in the calculations we've been doing with copper cluster theory, we use the copper cluster many-body method. It uses just some few hours to iterate to a good ground state, but to calculate the matrix elements can take up to 2 days.
Yeah. But if you're going to use that table for 10 years,
then
2 days,
you just get it. Yeah, exactly. Should we take a small break? And then we just stretch leg for some 15 minutes. Is that okay? So what we have is an equation now, which is rewritten as an eigenvalue problem. But the problem which we have is that we don't know the coefficients. And the standard procedure then is to set up an iterative scheme where you start with a guess for the coefficients. And then with a guess for the coefficients, you can then calculate the matrix elements. So clearly, if your basis is a basis which is an eigenbasis of H0, then this matrix element here is easy to calculate. On the other hand, if you want the contribution from the potential here, and you want to plug that one into the diagonalization problem, you need to have a guess for these coefficients. And the standard guess is actually the standard first iteration would simply be just to put these matrix elements to a diagonal matrix elements where they're just equal to 1. So that means it's only the diagonal term which enters the first iteration. And that's pretty easy. And then when you have that one, you would then keep iterating, because every time you diagonalize, you get new coefficients, Ci alpha, and the new ones you get, you would plug them back in here. And keep in mind now that this summation here runs over all the single particle states you have. But then the size of the system is then reflected into this term. So this reflects the actual number of particles. So we should put an n on top here. So this is normally called a density-dependent term because it is proportional to the number of particles which you have. Whereas these terms here, the next ones, they are defined, the summations here, they are defined by the basis you have chosen. So you can have 10 states below the Fermi level which occupy 10 particles, but you can have 1,000 single particle states gamma delta. And you can obviously let the calculation run also for the other states. I mean, you don't need to calculate the J's and so on only for states below the Fermi level, because when you're setting up your problem, it's most convenient when you're setting up the problem is actually to do, so let's look at the algorithm here. So we assume that we can pre-calculate these matrix elements, and they are tabulated. Pre-calculate and tabulate with a given basis. The matrix elements alpha, H0 or beta, and so somewhere there's a table there, and alpha, beta, V of gamma delta, anti-symmetrized. So this is just a table you would look up. And then you need to obviously then define how many particles you have. So you need that, define the Fermi level, F, and that defines also the number of particles. So you can always define the Fermi level in terms of the lowest lying occupied states. And then you would have an iterative procedure. You need also to set up, define these coefficients Ci alpha, and we're going to put a 0 here. And the standard choice is the first iteration, a typical choice then. Is that you have a Ci alpha of 0, which is equal to delta I alpha. So just a diagonal element. Now, when you're setting up the equations, you should set up the equations for states both below and above the Fermi level for the new basis as well. So that means that the problem becomes symmetric in the number of single particle states you are including in your Hartree-Fock calculation. So that means in principle, what you need now is to set up H of C of P, that's why we use the P here, of Hartree-Fock. So this is your Hartree-Fock Hamiltonian, which is then given by some epsilon P of HF of psi of P of HF, and where P now runs both states below and then above the Fermi. So P then contains now the states below the Fermi level, I1, I2, up to some In, and then it has states above the Fermi level, which would then run from A1 up to some A, which we call for D here, which is the last single particle state we have. So the dimensionalities of the two problems, the non-Hartree-Fock basis and the Hartree-Fock basis should be the same in terms of single particle states. So then we will simply end up setting up these equations. And the thing we need to do then is just set up this iterative scheme. So when we've done these definitions, then while convergence criterion not met, and the simplest way of doing that, the typical convergence criterion, is that you have the epsilon Hartree-Fock, the single particle energies. So let me just put that like this. Epsilon Hartree-Fock for iteration n plus 1 And now you're summing up all the single particle energies, epsilon p here. So this is actually a norm 2 or a vector, which contains all the single particle energies, minus epsilon p, Hartree-Fock, of n, like this. So while that is not met, then what you would do is to diagonalize, calculate, and then we will calculate this h, Hartree-Fock, which is given by the equation which you have up here. So this specific quantity. So you would have now an h, Hartree-Fock, as a function of a given iteration. And you see now that if you put these matrix elements to diagonal ones, that means that what you would have here would simply be a sum which runs over the, so your j here would be equal to a gamma. So you would simply have a sum over gamma and delta in this specific case, because then you would just have diagonal matrix elements. So the first iteration, if you pick these matrix elements, the 0th one, to be equal to just a diagonal matrix, then you end up with simply having a sum over gamma and delta, and the sum over j disappears. And that means that you can simply calculate this set of matrix elements as just a sum over the alpha and beta values, which you have here. And these gammas and deltas will run over all the matrix, all the single particle states you have. So that's a typical choice for the first iteration. So then you would simply calculate C, and then I'm just going to write it like this. And this is equal to epsilon Hartree-Fock. And then I skipped in the subindex P. And this is for iteration I, multiplied with the C of I. And then you obtain new eigenvalues and new eigenvectors, where you have, when you have set up, oh, sorry, I was a little bit rushed. That was a little bit too fast here. So first you calculate, yeah, this is one. I was thinking of the next step, H Hartree-Fock for iteration I. And here is, no, so N, iteration N. And then you calculate, you diagonalize. The new eigenvectors. So you have an HF of iteration N. You get the new coefficients for this specific iteration now, because the this Hamiltonian here, the Hartree-Fock Hamiltonian, is calculated with the previous values you had. And this is equal to the epsilon Hartree-Fock for that specific iteration multiplied with C of N. And then you would continue this till your convergence criterion is met. So for every iteration, you need to calculate this matrix. Now, if you now look at the diagonalization piece, that gives you immediately the energies, and then you can confront the energies with the results from the previous iteration, which means this quantity here. Now, there's a reason why you put the convergence criterion here and not on the total energy. So if you look up a little bit to the equation for the total energy, you could actually have a iteration loop where you now calculate the total energy. But if you now look at the expression for the total energy for every new iteration, then these coefficients would depend on the iteration. But now you have a loop with over 4 indices. You have to loop over I and J. Here you have a double loop, and you have to loop over I. So you have actually 6 summations and 3 summations there. And that's numerically very expensive for every iteration. So typically people will do the convergent test on the single particle energies, because then the only thing you need to do is to calculate this one. And for every iteration to calculate that one means that you have no loops here, and then you have a triple loop here. One over all the single particle states, actually 2 over the single particle states and 1 over just the states below the Fermi level. So from a computational point of view, this is less computational consuming. And also what you can do when you have the new coefficients is that you can rewrite them. We will see that next week when we are going to look at how we implement it. You can actually recalculate this one in terms of efficient matrix multiplications. So you can actually set this up as a matrix, and you can also set this up as a matrix, and then simply perform efficient matrix multiplications. So that's pretty efficient to perform, or you can just loop over the states, and then diagonalizing, you would typically then have from 100 to 1,000 single particle states, and that's a matrix which is pretty easy to do. This is the Hartree-Fock algorithm.
And if you're not converging, would you try like randomizing your starting point?
Oh yeah. So this is also something which can be done. The way you start your initial set of coefficients is up to you. This choice which I gave you is a pretty common one. You can randomize it, but you have to make sure that the matrix is unitary.
Yeah.
So these CIs make up a unitary matrix. That's the only constraint which you can have. We should have to have.
And it's also good to have it diagonal, right? Because then you can see more quickly if it's converging.
Yeah. Okay, so this is the algorithm, and one of the things which we will discuss a little bit later when it comes to applications is how we actually set up the Hartree-Fock equations, because you can have Fermi levels where you fill up all the single particle states with spin up and spin down. So you have an equal amount of spin up and spin down particles. Alternatively, you can have Fermi levels with different types of spin up, different numbers of spin up and spin down particles. And that's something which we will often use for open shell systems. So we will mainly stay with a system where you fill up all the states to the Fermi level, and that there's only one slated determinant. And that leads to something which is normally called restricted Hartree-Fock. And this is basically what we will cover in this course. Now, there's something which I wanted to mention, which has the name of a theorem, but it's not exactly a theorem, but it's called Koopman's theorem. And you may have heard of that one. It's not a theorem by itself. I'd rather say it's Koopman's approximation, but let's stay with what's normally found in the literature. And this is an interesting way to interpret energy differences between a system where you have removed one particle. And so let me just bring that up, the definition of Koopman's theorem. So one of the things which we can do then is actually to think of the Hartree-Fock calculations where we have removed one particle, and we have removed that particle from a specific single particle state. So assume now that you have removed, so we have removed a particle, and we can add a particle to a single particle state actually as well. So there are two equations which we're going to look at, and this allows us to have an interpretation of what these Hartree-Fock energies can mean. So assume now that we have removed a particle from a single particle state below the Fermi level, from a single particle state, and in fields like atomic physics, molecular physics, and also nuclear physics, this is very much used as an approximation from a single particle state below the Fermi level. So this is the variant where we move one below the Fermi level, and then we can also add one on top of the Fermi level, below F. And we are going to rewrite this one as E of Hartree-Fock. This is the total energy of the system. And we write this as N minus, and this is a kind of co-notation. We take away a particle, but we have removed that one from the single particle state K. This is the way you should read that kind of labeling here. Now, what that means when we look at the equations which we had for the energy, this is the same as taking the previous sum, but we have I from 1 up to n. And then we have an I which is different from k. So k is not included. So we have taken it out. So we are simply assuming now that this energy given by H0 of I here, simply done sum over the state which has been removed. So it's an n minus 1 particle system. And then we have plus 1/2. And then we have the sum over I and j. And we have I different from k and j different from k, obviously, multiplied with, and then we have the matrix elements ij, v, ij. And if we don't want to use this anti-symmetrized sign, we can write it fully out in terms of the exchange and the direct term. Now, if you look at this one, this is something which we can now rewrite in terms of the following. So this is the same as the original energy, the E Hartree-Fock of the n particle system, but where we have subtracted one contribution. So this will be minus, and then we have the state k of H0 of k, right? So I'm just taking it out.
Oh, wait, is the order above correct? When you multiply by ij, v, ij, you subtract ij, v, ij as well.
Oh, sorry, this is the exchange terms. Thanks for seeing that. This is actually ji here. Sorry. And then, but let's just, so what we would get then, when we take it out, you have to be careful because we have a sum over both I and j. So we would have a sum over I equal 1 up to n. And now I have a matrix element, and I'm going back to the anti-symmetrized matrix elements of ik, anti-symmetrized. And then I have minus 1/2, and then I have a sum over j equal 1 up to n. And then I have kj of v of kj, anti-symmetrized. Now, if you look at what we have here, we can bring this together again, the two ones, because we just changed the dummy indices and then we use the symmetry of interaction. So this would simply be E of Hartree-Fock of n. So that's the equation which we have been optimizing. Minus, and now I have this k of H0k. Then I can rewrite this as a minus. Then a sum of I up to n. So this is a sum of the Fermi level of ik, v of ik anti-symmetrized. Now, if you now look at the last term, how would you, if you look at the two last terms, which we have, this term here and that term here, what is this actually equal to? Let me give you a spool back a little bit and take a look at the equation for the Hartree-Fock Hamiltonian, right? But now this is written in terms of, so remember that let me just give you a hint here again. So we can rewrite in the new basis, which we have, the H Hartree-Fock Hamiltonian of PQ is given by P of H0 of Q plus a sum over J less than the Fermi level of P of J of V of Q of J anti-symmetrized. So if you look at the two last terms, what should they correspond to?
Yeah, very similar to the last.
Yeah. So this would actually be the Hartree-Fock energy for the state K. So this is actually equal if you think of the Hartree-Fock Hamiltonian acting on a specific state. So this is PQ, means that we have specified the matrix elements. So we have defined the Hartree-Fock energy for that specific state as a K of H0 of K plus the sum over I equal 1 up to n, or less than the Fermi level. And then we have k of I and v of k of I anti-symmetrized. So what I have then is that this E Hartree-Fock of n minus 1, where we have removed a particle from the level k, is the same as this E Hartree-Fock, so n particles, minus epsilon k Hartree-Fock. So if we are to measure the energy difference, so you could now think of these as quantities which would be measured experimentally. So you can often measure the masses of particles, or let's say nuclei or atoms or whatever. And then you can measure the mass of the 1 minus k, and you can translate that one into what's called a binding energy, and you can actually calculate binding energy differences. And then you could compare these experimental quantities. If you think that your Hartree-Fock calculation is close to experiment, then you can think of your Hartree-Fock energy as the energy here of the removal of a state of a particle below the Fermi level. So that means that the energy difference between the two systems can then be thought of as you being able to knock out one of the particles below the Fermi level, and that this energy should then be equal to the Hartree-Fock energy. So you can relate this immediately to experimental data. So for the whole state case, this is a state below the Fermi level. So we have that this epsilon of k Hartree-Fock now is actually equal to E Hartree-Fock minus E Hartree-Fock of n minus 1 particle in the state k. Now, this is something which this is actually Koopman's theorem for states below the Fermi level, but it should never be called a theorem. It's an approximation. So if you now look at these equations, could you think of, if you think physics-wise, let's assume now that you have run a Hartree-Fock calculation. And if you look at the assumption here, which we have made an assumption that the Hartree-Fock energy for the n-1 particle system can be calculated with the same single particle states as in the n particle system. So if you take a look here, suppose I run a Hartree-Fock calculation for a system with n-1 particles. In principle, these single particle states should not be the same here as they are here, because it's a different system. So if you think now more physics-wise, if you do this in atoms, in molecules, do you think this sounds like a reasonable assumption that the single particle states don't change for electrons? So what's your feeling about the physics of the system? So an atom has an electron or number of electrons which move in a field which is set up by the atomic nucleus and the other electrons. So this electron sees an effective charge. It doesn't see the full charge of the atomic nucleus, the protons, but it sees a modified charge. We don't have the exact single particle wave function because we haven't solved the many-body problem exactly. So we have an approximate solution. But if you think of atomic physics, do you think that these single particle states for electrons would change much from a n-1 electron system and a n electron system?
The field is not the same, right?
The field is not the same of the electrons. But which one would you expect would be the dominating part of the, in atomic physics, the dominating part to the energy from the Hamiltonian? Any feeling about that? So we have three pieces. We made an approximation. Electron-electron repulsion, the attraction from the atomic nucleus, and the kinetic energy of the electrons. Which one do you think would be the one which is more important if you look at the potential energies?
Probably the electric one. The electric one?
Yeah, because we have made an approximation in the system, right?
Yeah.
And the approximation is that the only parts of the Hamiltonian contain kinetic energy from the electrons. We assume that the atomic nucleus is at rest almost because it's much heavier than the electrons. We have the attraction from the atomic nucleus, which binds the electrons to move around the atomic nucleus. And then we have a repulsion between the electrons. So if I take away one electron among, let's say, 10, do you think the motion of these electrons will be strongly affected or
Not much, I think.
not much? Exactly.
They will still bind it probably.
The atomic nucleus hasn't changed. So this is the same as you taking sodium, which has 11 electrons, and you kick out an electron. So the other electrons, they see the same atomic nucleus, which has charge 11, and that gives the largest contribution to the energy. So Koopman's theorem is not exactly a theorem, but it's an approximation. So this approximation works well if the field which the particle sees when you take away one isn't that much changed.
At what point did you do the approximation? Because now you just put equal signs all the time, but
No, here I just say that this energy is now given by the same single particle states. So in principle, I should have run a Hartree-Fock calculation with n-1 particles and not n particles. But I'm using the approximation I make is that this single particle basis for n-1 is the same as a single particle basis. That's the only way I can make these calculations. If I don't make that approximation, so that what I'm saying is that the single particle field doesn't change from n to n-1. Because else, what I would have had then would be an I tilde here, an I tilde, and I tilde, and then I couldn't make these kind of calculations which I don't. So this can be useful in many cases where if you assume that, then you can actually make a physical interpretation of the Hartree-Fock energy as the energy which is required to remain a single particle state below the formula. So in atomic physics, this is called ionization energy. And if you run a Hartree-Fock calculation, you can go and look up the experimental ionization energies and see if they differ a lot. And in atomic physics, what we will see is that they do not differ that much. So that tells you that this mean field is an okay approximation to your system.
And asymptotically better.
Yeah. And it gets better and better when the nucleus becomes heavy and heavy, the atomic nucleus. So you can get a lot of this kind. The reason why this is also interesting is that suppose now that you replace this quantity and this quantity with the experimental binding energies. So you look up tables of experimental energies, you do the subtraction, and then you go and look up your Hartree-Fock energy. And that is pretty close. That means also that this Hartree-Fock procedure brings in important correlation for that type of system. And you will often see that if the interactions between two particles is not very strong. So there's a lot of physics which you can use in connection with Hartree-Fock theory. And this is actually our first, how to say, encounter between experiment and the theory which we are developing.
So it's also dependent, it's not only dependent on the number of particles you already have in the system, but it's also dependent on which particle you are removing.
Yes,
right?
yes, exactly. That's also an important statement. So this works well for states very close to the Fermi level.
Yeah, because here we are not making any assumption.
No. But when you are looking at states very deep down into below the Fermi level, then this approximation is not that good. But if you're looking at states like if you think of sodium, you have one electron in the 3s orbital, you have filled the 1s, 2s, and 2p orbitals in atomic physics, and you have a single electron which is weakly bound. That's why sodium reacts so well. because that electron, these are the alkali, no, the not alkali metals, what's the name of them?
No, isn't it?
Yeah, it's alkali metals, right?
I don't think so.
Yeah, so you have the lithium, sodium, etc., gallium, etc., etc. Yeah. And the potassium, actually, not gallium, potassium. Yeah. And that just continues with just one valence electron on top of it. And they are weakly bound. And then Hartree-Fock theory gives a decent approximation. So you can repeat the same exercise by looking at you adding one particle. So if we do the other one, so we could now add one particle. I'm just giving the result because it's the same mathematics which we're doing. So adding one particle. What you will see then is the following. So we would have epsilon A Hartree-Fock. Is then going to be the difference between the Hartree-Fock result with us having n plus 1 in A minus the energy Hartree-Fock of n. And then you can go back again and say, okay, I know the experiment. If I know the experimental values, I can then compare this number with the experiment. And this also works best for states near the Fermi level. And it's a very good approximation. And it's it allows you to start interpreting your data compared with experimental data.
Is it possible to know the error?
Oh yeah, no, you can. So the error, you would have many sources of errors. So one clearly is a Hamiltonian because you've taken away the nuclear degrees of freedom. If you look at atoms, your result will depend on the number of single particle states you include. So the energies. So one thing is a convergence criterion you set up in the Hartree-Fock method, but you will also have to test that as a function of the total number of single particle states. So that's actually a very important convergence criterion. And in addition, you don't know whether you're running with the correct Hamiltonian because you made approximations there. But if you can calculate the matrix elements to numerical position, and then your method converges as a number of single particle states, then you would say that, okay, possible errors of divergence between experiment and what you're doing is due to other many-body correlations. Normally, you cannot nail down the error precisely. So actually here, you will have pretty many sources of errors. One is a truncation in single particle basis. The other one is a truncation in your Hamiltonian, which terms you retain. And clearly, the other ones are missing many-body correlations. And this is actually what the coming many-body theories are about, how to gain correlations beyond Hartree-Fock. So all the methods which we typically end up using, they're called post-Hartree-Fock methods. So you can think of Hartree-Fock theory as a kitchen item, which gives you a better basis, and hopefully something which is closer to the true expectation value of the ground state. And then you use these basis functions to do either FCI, which we discussed previously, many-body perturbation theory, coupled cluster theory, or any of the standard many-body methods. So you reduce everything to coupled single particle equations, and it's a very easy and efficient way to implement it. And you can think of it really as a kitchen item in many-body physics. Okay, I'm going to stop here. I was hoping actually to run into the Lipkin model because we are going to use this Hartree-Fock theory on the Lipkin model. So that will be the exercise for next week. Then you get some time to practice by just varying these different coefficients. And with the Lipkin model, when you, now we can wait with that for next week. And I can actually discuss that next week. Because then you can derive the stability of the Hartree-Fock equation in terms of the strength of the line interaction matrix elements. So that allows us to gain some nice insights about the relation between the different parts of the Hamiltonian, like the single particle piece, which we have here, and the strength for the interaction matrix. And next week, we will also discuss more formally the stability of the Hartree-Fock equations. And I was also thinking that next Friday, I would like to present the kind of first midterm, which we have. And then we just put a deadline for just roughly a week. So we can start with it this coming Friday, and then we just dedicate Friday to work on the midterm. Okay, I'm going to stop the recording here, and you will obviously